Hello. I'd like to do another example of arrays, so hopefully you'll get the feeling for them. What the problem's going to be this time is I am given a list of positive integers and the size of the list and a number to search for, to find in the list. The program of determine if the number is in the list. I could go further and say also print out where it is in the list. That wouldn't be much of a difference. Now I've created the list already. So as an example, suppose the size of the list is 16. And the list is, and now I have to go and get it. Hold on. So I'm going to do a Control-C and then bring it back here. And I'd like to get it on one line, so I'm just going to bring it down just a little. There, that fits. Now, you will notice that I left out a vital word up there. I want a sorted list. And the sort in non-decreasing order. So as you can see, some people call that increasing order. The only difference is that if there's a duplicate, increasing order doesn't cover that case. And I wish to determine if 419 is in this list. Now you and I can look at it, but the computer's got the list stored someplace and it has to go and find it. Now the worst possible way I could think of doing it would be the following. One bad method. Compare to 113. Compare to 132. This would actually be, let's say, list 0 equals that, and this would be list 1 equals this, and then I would compare to list 3 equals 148, and I'm moving along. Now I would compare to list 4, which equals 186. Then I would compare to list 5, which equals 189. I think I'm I haven't made any mistake. Well, I left out 2. I knew something was wrong. I could tell. 4 equals 189. And then I would compare to list 5 equals 244. And I would compare to list, now I made a few mistakes there, to list 6. List 6 equal 564. Now, let's look at what that means. Did I put all of them right? 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Which is larger than 419. If 419 is in the list, it would have appeared already. Let me get that down. It would have appeared already. So, 419 is not in the list. Now, this particular kind of sort, this is called a linear search, because it goes one by one, just like you're following a line. The average number of places we have to search before we know whether 419, whether a value is in the list is, now let's think about this. Let's assume that we have a random set of numbers we're searching for. So they could be anywhere within this list. Well, on average, some of them are going to be in the first place. In fact, some will be we'll know by the time we look at the first one. Some of them will have to look all the way at the end. Some will have to look at the first 2 places. Some will have to look at the last 2 places. So if we average all the numbers of places we have to look, then we should get the size of the list divided by 2. Because theoretically, probabilistically, the number of times we only have to search one of them is the same as the number of times we have to search that one. Then we have 2 of them is the same as the number of times for this one. So approximately we can say size divided by 2. Now, that's not very good. For a list of, let's say, 100 million values, we need on average, 50 million searches, or I should say comparisons. We have to search. That was what I wanted. And this is another way of putting it better. Now that seems rather prohibitive. You and I might not have 1 million things to search, or 100 million, but the IRS does, and I'm sure many banks have a lot, very large number of records to search. So what do? It just seems to be too much. This is an example of a problem which we have a good algorithm for. We know it works, but the algorithm just doesn't scale up well. That is, as the size of what we put in the algorithm grows, the time the algorithm takes gets longer and longer. We don't like that. You'll find out next semester that that's called the complexity of the algorithm, the amount of time it takes. And we represent the complexity as a function of the size of the input. In this case, we can use how many items are on the list, and we'll say that for size number of elements, this algorithm takes 1/2 of the size. But we'll ignore the 1/2 and say it's linear. As size grows, it grows as size grows. So can we do better? Well, let's take another possibility. Let's take this example here again. Let's see if we can do it better. And you already know how to do it. You might not know you know how to do it, but you do. Let's think for a minute here. If this were a telephone book, they still have those, maybe, and you want, or a dictionary, I think they still have those, and they haven't all been replaced by what's on the web, then I don't think you'd start searching in the middle of at the first of this list to find something. I suspect you'd jump into the middle and you'd say, oh, 419, it isn't 614, but it's smaller. So I'll look at this side and ignore everything above that side. And then in this half, I'll jump in the middle of that. Oh, it's not 189. It's bigger than 189. But it's smaller than 614, so it's caught in here now. And I'll keep doing that until I come to it. Each time I do a search, I'm doing a comparison, I'll cut the number of elements that could be 419 in this case in half. Now, in half is 1/2. And when we do things like that, we call things binary. So we're going to do a binary search. It's not that hard, but it does take thinking ahead of time. I keep telling you that you have to think out your program before you do it. You have to know how you're going to do it. This is the thinking out right here. I'm going to suggest the following. What do I know right now? Well, I know the left. If left equals 0. And right equals 15, which remember is 16 minus 1. Then, if 419 is in this list, it is between list left and list right, inclusive. That means including the endpoints. Well, I don't think you can argue that. Basically, what I'm doing is saying, if it's in the list, it's in the list. I'm starting at the beginning of the list and going to the end of the list. Okay, we know that now. Well, why don't we do the following? Let mid equal left plus right divided by 2. Now, in our case, that's 8. 0 plus 15 divided by 2. And by the way, I wouldn't have cared if it had produced, if the numerator had been odd, because remember, I truncate. So there's no problem here. Now, I'm suggesting the following. We are going to compare 419 to list mid. This mid is the 8 element. That's 0, 1, 2, 3, 4, 5, 6, 7, 8, which I believe is 614. Now, again, to make sure, there are 9 elements there. You may say, well, that's the 9th element. No, remember, we start counting at 0. Okay. 419 is less than 614. If it is in the list, it is between list left and list, well, this was mid minus 1. Now, we want to keep a loop going. So what we're going to say is, now, let right change be mid minus 1. We've just changed it. We've decided that it's that, and in our case, that's 8. So we know that there are only 8 possible places. There are only places between 0 and 8 where it could be. And pardon me, it's not 8, it's 7. I made a mistake there. Well, now, being good computer scientists, we've just done something once. Why don't we do it again? So let mid equal left plus right divided by 2. Well, I get 1 plus 7 divided by 2 equals 4. I rigged this. I gave you size 16. Any size would work. You'd just be cutting things. You'd be chopping off parts of it when you've got odd numbers in the numerator. Well, now, obviously, the next step is to compare 419 to list mid. Now there's a possibility it equals it, but I don't think it does in this case. The fourth one is 0, 1, 2, 3, 4. I count 189. 419 is greater than 189. So if it is in the list, it is between, and again inclusively, I'm going to get myself a little room here. There we are. And I think I'll pull this one up and this one up and even this one. But here, I won't move that up yet. I will move this down. Yeah, let's leave it right like that. Now, this time, it is between list mid plus 1 and list right. Moves up. So that means we'll now let the left side move. Let left be mid plus 1, which equals, see, mid is 4, so it equals 5. We know that this value, if it's in there, is between list 5 and list left. List right, and list right is 7. So we do the same thing over again. Let mid equal left plus right divided by 2 equals left is 5 and right is 7. So that's 5 plus 7 divided by 12, divided by 2, equals 6. So compare. Compare 419 to list 6, which equals 0, 1, 2, 3, 4, 5, 6. I get 564. This means that 419 is less than 564. So we're going to move the right side. It's not above 564, so it's got to be to the right of 564. So we're going to say that the right side equals mid minus 1. Now we did that once already. I just didn't emphasize it, but we did it. And we know that if 419 is in this list, it is between list. Now, the left-hand side is 5, and the right-hand side is 5. Left and right are both 5, aren't they? It looks to me like we did that right here, mid minus 1 equals 5. Well, how about let mid equal left plus right divided by 2 equals 5 plus 5 divided by 2 equals 5. Compare 419 to list mid. List mid equals, see, it's the 5th one. I'm gonna keep moving it up. It's number 5. 0, 1, 2, 3, 4, 5. I get 244. So this is 244. 419 is greater than 244. Therefore, it's to the right of 244. So we have to move the left up. So left has to equal mid plus 1, which equals 6. Now we know that if 419 is in this list, it is greater than or equal to list 6, because that's the left side, and less than or equal to list 5, because that's the right side. But wait a minute, that's impossible. This is not possible. Because we know that list 5 is less than list 6. They're in order. So it's not in the list. 419 is not in the list because, now we have to look, why? Why did that happen? Why? What can we look at? Well, let's compare left and right. Left is greater than right. Remember that we move left to 6 and we have right at 5. Now, that seems kind of doesn't quite work. We move them that way. That means we're done. Now there's the algorithm. Let's, for the fun of it, look at how many comparisons we made. We compared once here, twice, 3 times, 4 times. We took 4 comparisons. I want you to notice that 2 to the 4th equals 16, which is the size of the list. Now, that's going to work basically for any size of the list. Let me just go one last line here. If 2 to the n equals the size, then we need n comparisons. Now there's a fancy name for that. N is the logarithm base 2 of size. And it could be point something. So it's not necessary that it's exactly equal. So let's take a look for a minute. We know that 2 to the 10th is 1024. And I don't feel like doing a lot of work, so I'm going to go over here and bring up just a blank one here, and I'll do equal to. Now there is a logarithm function here. I'm not going to try it. I'm just going to go this way. 2 to the 20th equals 1 million. 2 to the 30th, oops, I need the equal in front of that. 2 to the 30th is just about 10 million. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's about 1 billion, which it should be. So if I take 2 to the 29th, that is below 100 million. 1, 2, 3. So for 100 million to search, where am I? I said we took 4 here. So the log of 100 million is 29 point something. I'll say it's between 29 and 30. We need about 30 comparisons. That compared to 50 million in the linear case. We can do 30 comparisons. 50 million comparisons will take us a little longer. So that's the kind of algorithm we want. We say that this algorithm is a binary complexity. It grows as the log base 2 of the size of the input. It's a better algorithm. Now in CSC 104, we don't worry as much about the complexity. You start worrying about that when you get to the 2 sophomore level courses, data structures and algorithms. And it's a very important concept. There are some problems where we just do not know if we have nice algorithms to solve them. We haven't found any, but that doesn't mean they don't exist. Maybe they do. But there's a huge problem in the theory of computer science called the NP=P problem. And the question is, do certain problems have nice solutions? Problems like the traveling salesman, and problems that business needs, like laying down pipe, for example, or telephone lines or cable lines. What's the best way to do it? So far, we don't know if there's a good algorithm. Now I'm ready to write the program. So let's close this solution and let's write a new program. And I'll call this binary search. And I will need # include. I don't think I need IOmanip, but I do need fstream using namespace standard. And I'll have an array, and I want the size, so I want the size to be able to vary. So I'll use my const int how many equal, in this case I'm starting with 16, but I could change that. Now I'm going down here, and first I'm going to declare an if stream, which I'll call sorted. I already have that file written. And I'll have sorted dot open C:// users / fp forward / spring 2021 / CSC 104 / sorted dot text. I used the same name, it was easier. So now, it looks like I have to do a couple of things. I have to first ask the user. Well, I'm going to loop this. I've decided to do this many times. So I'm going to begin by declaring left, right, and mid. And I'll also have what to find. So what am I looking for? And I'm going to repeat while 1 equals 1. That just means forever. I'm going to ask the user, what do you want to find? Now, if you want to, I can make it a little easier. I can stop what to find at, something like equal 10,000. And what I'll do is I'll say, while what to find is greater than 0, because we're looking for positive numbers, remember? And I'll say, what do you want to find? Negative stops program. This gives the user a way out without having to rely on killing the program. So I'll put and you usually put it, you tell the user how to get out. And so we'll just cin what to find. And I think I would also I need a list. So I'm going to have list how many. And the first thing I'm going to do is read in the list. So for int I equals 0, I less than how many, I plus plus, sorted, list I. That's that. They're in. I actually think I'd like to see those numbers. So I think what I'm also going to do is print them out as I get them. So I'm also going to see out list I, and I'll put a space between them. And at the end of that, I'll have my cout, end out. That way I can see it. I can see what's there and see how much I need to do. So there we are. I now have what to find. Well, if you look back at the algorithm, the first thing we did was set left to 0, right to how many minus 1, because remember there's a 15th place but not a 16th place, and then we started our loop. So what I'm going to suggest is while the left-hand side is less than or equal to the right-hand side, do the following. Compute mid equal left plus right divided by 2. If what to find, and I didn't quite emphasize this when I was doing the algorithm before, but there is a case we find it. So if it should happen, the list equal list mid, then I think what we should do is print out cout what to find is at location and then mid end out. Now, we don't want to keep going. We just found it. Instead of putting a Boolean in, what I'm going to do this time is just break. Break gets me out of the closest while loop or for loop. The closest one is the while left is less than or equal to right. Now, the second possibility is that what I want to find is less than list mid. Now, in that case, what I need to do is I need to move something. It's less than mid, so the right has to move down. So I'm going to say right equals mid minus 1. And that's all I have to do. Else, and notice I did not put an if, because I know the answer, left equals mid plus 1. Now, I always have to think that, am I doing this right or not? It's always, I have to make sure of this. If the number is less than the listed number, then I have to, it's on this side, it's on the left-hand side, I have to move right down. Otherwise, I have to move left up. So that looks right. Now, we keep doing that. If we get out of that loop, then I ask myself, if left is greater than right, then cout what to find is not in the list. \n there. Now I want to do it again. Well, let's see. I want to do it again. Actually, there were, I'm just going to go right back up to this while, and that'll read in the next one. so there's no problem. I just have to make sure I've managed to close everything. So this goes away. This whole thing down here goes away. This goes away. Now I can pretty well tell you if I've closed them. I'm going to put a brace here. If it's in the first place, then the machine thinks I closed them. So let's see what happens if I run it. There's bound to be an error. I knew it. I knew it had to have an error. Missing syntax, semicolon missing on line 30, it looks like. Line 30. I don't see it yet. Maybe I got it wrong here. Let me double click on this. All right. Semicolon missing. Oh! I had that twice. That did it. And something else. 42. In the file found. So I do not have matching. The match did not work. So there's one here. Open 2. 1 is open. 2 are open. 3 are open. 4 are open. 3 are open. 4 are open. 3 are open. 4 are open. 3 are open. 2 are open. 3 are open. 2 are open. 1 is open. And I thought, it looks to me like it matched. The machine says that 40 is the problem. So I'm going to look again. This one matches that one. This one matches the while way back. That matches that. That matches that. There's something wrong here from the looks of it. Why is it complaining there? There's a good reason for that. Again, that line was a mess. Okay, that takes care of it. All right, we have the list now. Let's look for 746. It's at location 10. Let's look for 21. Not in the list. Let's look for 702. Not in the list. -1. Gonzo. So we got it to work. That's a nice little problem. What I like about it is it gives you a good exercise in playing around with digging into a list, digging into an array. So we will put that away here now. I will copy it into here. There it is. And I will now send this and the video to you. See you later.